All right, let's get started with another example. So the whole point of these exercises is now, rather than sectioning our beams, a gazillion times to determine what the shear loading is, for example, in this case, or the internal forces are, um, we want to actually be able to do this in a little bit more efficient way, right? And hopefully in the first introductory example from the previous video, you saw that really there's only a couple of places where we need to actually section our beams in order to understand what the internal conditions are. So here we're asked to draw a shear diagram, which essentially means determine what is the internal shear loading along the whole length of the beam, right? And identify where it changes. So for these, of course, the first thing we're going to need to do is go ahead and find the support reactions and make sure we have all the extra information needed. So I have that free body diagram set up, ready to go. This is something we should be pretty quick at now. And we can go ahead and look at these and see, again, right away from most of these examples, sum of forces in the x will show us that the ax is actually equal to 0. And we can do sum of moments about A, right, and calculate for By. And let's call the full length, you can see up in the top right, moment arm would be L, minus P that has a moment arm equal to A, equals 0. We can go ahead and solve that for By equals P times A over L. And we know A, its distance is given here. A is equal to 3 times B, so A is 3/4 L. And so if we substitute that in, so we know A is equal to 3/4 L. So therefore By is equal to 3/4 P. And now using sum of forces Y, we see that AY plus BY minus P equals 0. We can solve this for AY equals P minus BY. We just solve for BY, so therefore AY equals 1/4 P. Okay, now the next step is actually to determine how many sections do we need. And what we saw last time, right, was that we know the shear is going to change any time the loading changes. And so I've kind of cheated a little bit and preset this up for us. But here, the idea, right, is that everywhere the loading changes, we're going to expect for the shear to change. So we're going to expect something here, here, and here. And of course, the shear will just jump up or down at the ends of the beam. So essentially what we have, right, is again, kind of like a section 1 and a section 2 over here, right, for x going from 0 to A and then x from A to B, for example, right? So let's go ahead and split this up into sections and take care of that. So we know we're going to analyze first a section with a cut, essentially, right, somewhere here in the middle. So I'll draw that free body diagram. This is valid for x going from 0 to A. Set that up, apply all of our loads. AY balanced by the internal forces and shear coming down, and then we have a moment. So we're just starting with the shear first, so therefore sum of forces in the y, AY minus V equals 0, V equals AY. We've already established that AY is equal to P over 4. So now it's a constant, right? So it's not going to change as a function of x, it's just a single number. And this is going to be true if I can draw on the shear diagram. I know that AY, starting from this point here, is going to be P over 4, and this is going to be true along this whole length. And then we'll see what happens at the discontinuity point where P comes in. So to do that, we'll look at section 2 and draw for a free body diagram for x greater than A. Let's scoot this over just a little bit. Again, we still have AY. We have our internal forces, V and M. And now we'll still apply P, right? But P acts at a distance A away from the left-hand side. And now, oops, If I write my equation of equilibrium for section 2, sum of forces y, I get the AY minus V minus P equals 0. So I know V is equal to AY minus P. AY up above was 1/4 P, so I know AY is equal to minus 3/4 P. So at this point, on the right-hand side, obviously I haven't drawn these very well to scale, but I know that this is going to come down here, and then this will be the case all the way to the end. Right. So I have a positive shear in section 1 and a negative shear in section 2. What about the moments? Let's set this up. So let's determine the M along the beam. And now we can use these exact same free body diagrams from up above, right? And now just solve using our moment equation. So if I do sum of moments at A for the left-hand side, I have M minus V times X, right? And so X is going to be this distance, right? Here. So minus V times X equals 0. So I know M is equal to V times X. I just established that for this section, section 2, the shear is P over 4. So I have again that the moment is a function of X. It's a linear function of X. The shear, again, we see this pattern starting to emerge. Here it's positive. I have a positive slope on the left-hand side, right? So I know that what I'm going to have over on this side, I should move this line down. Beautiful, the magic of technology. So for the moment, I know I have a linearly increasing moment that goes like this, right? And to what value? I can substitute X as 3/4 L, and now we get that moment there. But let's leave the equations as analytical ones for right now, and then we'll substitute at the end. Now we'll solve for the right hand, section 2 essentially, this one right here. We're going to use this free body diagram right here, and now solve for the moments at A, about A for this side. And in this one, we're going to need a little bit more room, so let's scooch this over. So now we have M again applied. Again, minus, and it, right, this is our X. But P is located 3/4 L, right? That scratching you hear is my dog wanting to come inside while I'm recording this lecture. So we have M minus V times its moment arm X. And then we have P, which is also a negative moment, P times its moment arm 3/4 L equals 0. Right, so we can substitute. We know shear now on this side is a negative, so M minus, just have to be careful with our signs here, minus 3/4 P times X minus 3/4 PL equals 0. So M is equal to still a negative, right? This is going to become positive, so bring it to the other side, minus 3/4 P, again a function of X, plus 3/4 PL. So hopefully the trend is starting to emerge for you, that when the shear is positive, we have a positive moment, and when the shear is negative, we have a negative decreasing moment. Again, always a function of X in these examples. Right? So we have that positive, negative, negative on this side. So we know this is going to be, for the moment, some decreasing slope. like so. Now what's the peak there? We can just substitute pretty quickly, right? Again, we can even do it a little bit. Oops. So here, if I use this one, where m when x equals 0, obviously then it's going to be 0. I can use this left-hand side equation, and I can substitute x equals 3L over 4. And so that's going to be P over 4 times 3L over 4. So I have 3PL over 16. And then when x equals L, I'll use this side. And I get minus 3 over 4 PL plus 3 over 4 PL, and voila, 0. So this peak over here, this value is the 3PL over 16. Again, with these same trends that we have a positive increasing, negative decreasing here.